You kept talking about turbulence as in trying to do some methods, deciding it wasn't going to do turbulence, and then simply saying, okay, this is a great method to go on in life. Now I want to go back to turbulence. What was it that so attracts you, and why do you think this is so important?
First of all, turbulence is all around us and in our bodies and in our environment and stuff. It's an important question of what's going on there. It's a purely mathematical question. It's a question, the equation unknown, and we seem to be unable to extract the information from the equation. So this is something which is an extraordinary challenge. Idea is missing about something which is all around us, and we should be able to understand. So it's unknowing, it's irritating. It's also, okay. Turbulence is fascinating. You can go look in the ocean, look at the water flowing. The variety of structures which are there are very interesting. It's also a prototype of other things. Much of our lives has this structure of a mix of structure and randomness. And that's what we live in. That's what makes our life interesting. If there were structures necessary, if there were no randomness, it would not be interesting. If you could understand something about turbulence, you could understand something about maybe some other philosophical questions which we have no way of dealing with. And that makes the problem extremely interesting.
Why do you think it has been so hard?
It's very hard because, again, we have no machinery for dealing with things which are with ephemeral, with what is the turbulence, which is an array of randomly generated ephemeral structures. There's no description of that which works. It's not. People thought of, there's all those things about fuzzy sets, about which you can't make, not applicable here. The other problems which have a mixture of disorder and partial order, as in spin glasses, but it doesn't seem to. I spent lots of time on that one, but doesn't seem to have much to do with turbulence, and there seems to be no prototype.
This is true because you get the idea of organization coming from disorganization reemerges with different names: emergent systems, global structure dynamics, etc. And there are things like Zhabotinsky waves and combustion and all sorts of places where it looks like small-scale things organize themselves on from simplistic games of life to real things. But how come, at least to me, they never make the leap over and say something about turbulence?
Because they're all low-dimensional. The thing which makes turbulence different is that all those chaotic structures, all those emerging structures, all that mechanism of which connected with chaos has an additional, very essential factor that the number of those, that the dimension is very large. And if you think of what, for example, the people talk about, chaos theory has been successful in describing flow between counter-rotating cylinders at moderate Reynolds numbers. But anybody looking at those flows, which are in fact chaotic, in this, exactly as chaos theory says, they are in fact laminar because the nicely predictable limited number of scales, it's not turbulent. So you have to add to this large number, the extraordinary complexity.
I think there's an even worse problem here, which is that a successful understanding of turbulence means not only do you understand how these small-scale, disorganized things interact and you get something big, but that you get something at the end that you can measure and then use to make accurate predictions, build structures, etc. And many of the models that seem to show how small-scale things become emergent big patterns, all you're supposed to do is say, great, this pattern looks big and that pattern looks big, so we're done. And I think successfully understanding turbulence requires more than simply an aha, look at the patterns, they look similar.
That's one of the shortcomings of turbulence theory, is that for practical purposes, if you really care concerned about designing things, the turbulence problem is conceivably solved. People have enough experimental data for, you talk to people in aircraft, they have experimental data and they've learned how to interpolate between them. And they don't need the theory. Except when you go, the only place we need a theory when you go into something like building spacecraft in which you reach Reynolds numbers for which there are no data, and then you may need some kind of theory. But for most application on Earth, you can do without the theory. So that limits the interest of turbulence theory, it limits the interest of the agencies in funding it. Also slows down progress.
Slows down progress. That I don't understand.
That slows down progress because, you see, anything in which people are practical people are waiting for the answers of what you do has a strong force driving innovation, driving investment, and forcing people to throw away obsolescent theories. If the clients are not clamoring for the answers, people the fact that some avenues of research lead nowhere does not necessarily kill them fast enough.
Okay, but there are very practical applications. You have a wind farm and you want to understand how the turbulence there affects whether or not you have a constant supply of energy from your wind farm or you've got to keep a gas burner going full time anyway.
The problem with wind farms, the problem is trying to predict the intermittency in the weather. And that, of course, is So that's a good question. But it's not obvious that people are going about it by simply using data, and it's not clear that you cannot get there by simply looking at data without any fundamental understanding.
So I think that's an example of what we were talking about earlier, which is data is fine except when you're talking at intermittent phenomena, rare events, etc. In which case, what do you do?
Well. I'm afraid turbulence theory will not contribute much to that particular problem. What will contribute to it is actually getting more and more data without fundamental understanding. So it's a tricky thing. I think my feeling about turbulence theory nowadays it's stagnating, and I think one of the reasons stagnating is that there aren't any clients clamoring for new answers.
Can you pose a client that would need a turbulence answer that won't be satisfied with data?
I'm not sure I can think of one. I think that using prior data has not been successful without also an trial and error component in designing, for example, re-entry vehicles from space or very large tankers, because the data were not available and people made mistakes and paid for them, but maybe they've done what they had to do. So I don't know. Okay. It's still a mathematical mystery. It's what's going on. Why? You look at the turbulent flow. What's going on there? How come it looks like this?
That problem appears in numerous different worlds, not just the turbulence. How does anything get organized and structure itself?
Yeah, but it's very much the same kind of problem. I mean, in biology, it's a big problem. How do structures arise?